All right, from the first part, we had this little gem, right? Actually, for the second part, Q enclosed over E naught is the flux. The total number of flux lines, imaginary lines, we're making up coming out of an object, correct? Yeah. Okay. We also know that by definition, the electric field times the area is in fact the number of lines I have going through it. The problem, of course, is the area itself might not be consistent with the electric field. The electric field might change over the surface area. You talked about that earlier, right? Say, well, what if the electric field is different? Like just because the net flux is totally uncalculated, if the charge is located closer to one side, there's more flux line coming to one side than the other side. So the area, the electric field might depend on the area, which means I can't just do area times the electric field. I have to do what instead? I have to integrate. So the flux is equal to the integral of E dot dA. Now the dot now refers to that which is going straight out. We talked about that before, right? It can't be, if it's going parallel to the surface, then that doesn't count, right? Because it's not actually leaving the surface. Agreed? Agreed. Okay. Now with that in mind, I'm going to add one more symbol. It's right here. This is only true if it is closed. What do I mean by closed integral?
Like finite bounds?
That's true, but not what I'm looking for. This is a qualification that says the following. It says you have to completely enclose the object, right? You have to completely enclose this charge we're talking about. You must have a complete shape. You have to count for all of it. It has to be a shape that's full. If it has a little gap in it, this doesn't work because lines can sneak out. Agreed? Okay. So the qualifications are the electric field, where I know what the area is, now it's dependent on the area, times the area, which requires an integral, over a closed interval. In other words, you have to have it completely enclosed. So far, so good? If all those are satisfied, then the following thing pops out immediately. Q enclosed over E naught equals the integral, the closed integral to E dot dA. This is worth 1 point on your AP test or 2. I'm not sure which. Depends on which version. So when you first approach one of these problems, the first thing you write down is that. You don't have to think. Just write it down. Get your 2 points or 1 point. It's the same thing. It means that which is in the same direction. Remember, area vectors are pointed outwards from the surface. So it's saying specifically it needs to be something that's going straight out of the surface. Normal surface. What? Well, we're going to need a lot of things. We need to figure out the area and stuff. So the first thing we're going to talk about is this. We're never going to use it in this form. Not once. You have to write it down. Because here's the thing. AP Central is concerned that you're not aware that it has to be completely enclosed. They're concerned that you might think that the next step is always true. The next step is not always true. In fact, it seldom is. How hard is this integral? Think about it. If I'm talking about imaginary flux lines where I've got it right next to the edge, right? I've got less here, that means the electric field here is going to be different than the electric field here, right? How are you figuring that out? You're going to cry a lot and throw up in your mouth. So here's what you're going to do for realsies. You ready for realsies? Yeah. The realsies is you're going to pick an electric field where it does not change over the area. What? That means I'm going to pick a shape where the electric field for every place on that shape is the same. If it's the same, I don't need to integrate it, right? Yeah. So therefore, I'm going to completely enclose it. I'm going to pick something symmetric so the electric field is always the same. And so the next line is always going to be, if you can calculate it, this. That's real Gauss's law. The charge enclosed divided by this constant is equal to the electric field times the area, assuming you pick a good enough shape to pull it off.
And that makes sense because E would be a constant if it's not changing, and then the constant would go outside the integral, and the integral would just result.
Okay? So far so good? All right. So, hence, if you have a point charge, or a spheroid charge, or a combination thereof, what is the shape you're going to pick? what would be symmetrically around it, where the electric field at all spots in the same would be the same? A sphere. If I give you a sheet of charge, if I give you a big old, infinitely big, huge, monstrous sheet of charge with charges all the way strewn throughout, evenly distributed. Distributed would be better. What shape I'm going to choose? This is not obvious. Because remember, you're going to have lines coming off this way and lines coming off that way. But if it's really big, you could choose any shape you wanted to a degree. And then what I would do is I'd pick a cylinder. Why? Because I can take a cylinder, I can cut a part of the surface, I can go down below. You have to go below as well, though, right? And you're going to do, that's going to be a shape you pick. Now, why don't I have to consider the size? If I'm close enough to the middle, the lines aren't curving out, right? So the lines here is going to be the same as here, so therefore all of it's going out the top and bottom. Is that 100% true? No, but it's true to the degree you're not near the sides, right? It's true to the degree if your sheet looks like this and your cylinder looks like this, that's pretty true. It's definitely not true if you're doing this. That's a bad choice. Then, because there'll be a lot of lines leaving outside, right? If there are lines leaving outside, this Gauss thing doesn't work. Gauss thing only works when that deflection doesn't matter. There's not much going out to the sides. If much is going out the sides, you have to go back to what we did at the start of the chapter, which is mathematically beyond us. So therefore, it's going to be one of those two things, right? It's going to be one of the four shapes or something to do with Gauss. Expect that. What?
How is flux useful?
How is flux itself useful? Because it gives us Gauss's law. Other than that, it does nothing. Like literally, this is what it's for. We just learned all this about flux, so we can do what? Set one set of flux equal to the other set of flux and drop flux completely out.
All right, so
honestly, in my own opinion, there should be a flux question on this test. Will there be? There can be. Sometimes they ask you to solve one side or the other side of Gauss's law. Thanks.
Wait, so charge enclosed
over E naught equals electric field times area. Electric field is huge for us, right? Because that gives us voltage, that gives us force, that gives us energy, it gives us all the things we want. This is how we calculate electric fields for areas of charges.
Okay, but this assumes that we can make a shape that encloses the entire
yes,
thing.
Yes.
Does it
Can
have
we
to
do one
be
more?
the entire thing?
No, it doesn't have to be the entire thing. It has to be, so for example, the next shape I'm going to talk about is a line of charge or a cylinder of charge. What shape are we going to pick? A cylinder. And you might be thinking, well, Mr. Redley doesn't have to completely enclose all this charge because there's charge out here, isn't there? Actually, Gauss's law says only that which is enclosed matters, right? So as long as it encloses this piece, that counts, right?
So you could theoretically make a really small shape that would work for anything.
That would work for anything, and you can assemble a whole bunch of them to find a charge for something that is much larger in shape, right? Or you recognize electric field is the same as here, right? So therefore, if I do this part and close this part, all I have to worry about is this little section here, and I'll have the electric field here as well as here.
Is that assuming a uniform distribution of charges?
Yes, it has to be uniform. Why? Because if it's not uniform, then what happens to my E? What happens to this?
Then it's dependent on the area.
Yeah. Where am I? Oh, no, I don't want to be there. I don't want to be doing that integral. Can't do it. We can't do that integral. Frankly, this is when you get in upper division physics. They say, okay, time to open the can on the electric field. And you're like, oh, no, please no.
That sounds good.
Upper division, junior year, they start talking about electric field distributions that are not symmetric. How do I model a charge that's not in the right place and figure out how to do this?
That sounds good.
It's it's a lot of math. I don't know if it's a lot of fun.
I like
No, I can't. We're not even. You would need another year of calculus where you can start to talk about what you have to do this.
I thought we'll cover that in like 15 minutes.
You know what a matrix is?
Yeah.
Right? You see matrices? They start to have integrals that involve matrices.
That sounds so much fun. Yeah. What? So much fun.
Okay? And integral.
Oh, that's like multivariate, right?
Right. And then everything has to go through a matrix on its way out the backside. That's a little beyond the scope of this class, both mathematically and for terms of physics, frankly, it's beyond the scope of this class. So let's start off. Let's do our first Gauss's law and see if we've got some fun. And by the way, Gauss's law, you think, oh, this is not so bad. Gauss's law has lots of fun associated with it too. We can do a lot of things with it. don't think it's as limited as you're talking about. Let's start with 11 though. Should be fairly straightforward.